In the last video, we talked about the extended Euclidean algorithm, and we saw that if you have two integers, then you can express the GCD of those two integers as the first integer times some integer plus the second integer times some integer. And one of the applications we'll see is this fact about prime numbers. So the fact about prime numbers that we'll prove, this is a very useful fact. It's used to prove the prime factorization, the uniqueness of the prime factorization of numbers. It's that if p is a prime number, and p divides a product, so p divides a product of integers a times b, then either p divides a or p divides b. So, for instance, if you have 5 and it's a factor of a times b, then either a or b is a multiple of 5. Now, this is certainly not true if p is not prime. So, for instance, if you have 6, okay, 6 is 2 times 3, but 6 is not a factor of 2, and 6 is not a factor of 3. Similarly, 6 divides 60, and 60 is 15 times 4. So you have 6 divides 15 times 4, but 6 does not divide 15, and 6 does not divide 4. So it is important in the theorem that we are working with prime numbers. So let's get to the proof. So we have a prime number p, and we know that it divides a product of integers a times b. And we want to show that either p divides a or p divides b. So when you're trying to show, in general, either something or something else happens, you can go about it by assuming that the first one doesn't happen, and then prove that the second thing does happen. Because either p divides a or p doesn't divide a, right? So if p divides a, we're done. Because we just need to show that either p divides a or p divides b. So if p divides a, well, there you go. There's nothing to prove. Okay. So suppose that p does not divide a. So we're supposing that the first thing doesn't happen. Then we need to prove that the second thing happens. So we need to show that p divides b. Okay, well, we know that if p does not divide a, so the GCD of a and p must be 1. Right? Because, okay, why is that? So we know that the GCD of p and a is either, so a prime number, okay, only has divisors 1 and p. So it's either 1, the GCD of p and a is either 1 or p, right? Because p is prime. But we know that p does not divide a, so p is not a common divisor of p and a. So the GCD of p and a is 1. And now, by the extended Euclidean algorithm, we can find there are integers m and n, such that this is an a. Okay, there are integers m and n such that am plus pn equals 1. Okay, right? That's just what the extended Euclidean algorithm tells us. Now multiply both sides by b. So we need to get we need to get b in there somehow. So multiplying this equation by b gives us abm plus pnb equals b, right? Now, look at what we have here. We have this sum abm plus pnb. Now, this first term has an ab in there, and this second term has a p in there. Okay, so by hypothesis, right, we suppose that p divides ab. So since p divides ab, and p, well, since p divides ab, it must divide abm, obviously. So and since p divides pnb, and if you have a number that divides two things, it must divide the sum of the things. So p divides abm. Okay, so p is a divisor of that, and it's a divisor of this. Therefore, it's a divisor of the sum. P divides abm plus pnb. But abm plus pnb is just b. So p divides b. And that's the proof. So notice where we used the fact that p is a prime. We used it here, right? That the GCD is 1. And then once we had that, we had the Euclidean algorithm. Okay, we used that here, right, to get this equation. And then once you had that equation, the trick was to multiply both sides by b, and then notice that you get a, b, and p as factors of the terms. And then that lets us finish the proof. So a pretty short proof, but an important fact about prime numbers. That if you have a prime number and it divides a product, it must divide one of the factors. And in fact, this definition is, this theorem, I mean, is used to kind of as inspiration or motivation for the definition of a prime ideal in ring theory. So if you take a class on abstract algebra and you learn about commutative rings, there's this object called a prime ideal. And the definition of a prime ideal is motivated by this fact about prime numbers. So in a prime ideal, if A times B is in the ideal, then either A or B must be in the ideal. And in the case of when the ring is the ring of integers and the ideal is just the ideal generated by a prime number, that is equivalent to this theorem. Okay. So it's okay if you don't understand that, but I'm just saying that if you take a course in abstract algebra, you will probably see prime ideals. And this fact is important for understanding why prime ideals are even called prime ideals. Okay, in another video, we will give an example of how to use the extended Euclidean algorithm to calculate the multiplicative inverse of a number mod p.